Good afternoon, everyone, and welcome to this session where we're going to explore the fact-based realities of AI-assisted coding. And today, we're going to look at both the good, the bad parts, as well as the slightly ugly. And we're going to start back in 1977. Because I recently got exposed to the promises of AI-assisted coding in an unexpected way. Earlier this year, I started a new hobby. I started to develop games for the following machine. How many of you have ever had one of these? Atari 2600. Beautiful machine. And I can promise you, it's quite an interesting hardware. I think it's fair to say it's not really LLM ready. Because, believe it or not, you have 128 bytes of memory available. However, you're compensated by a full 4K of read-only memory. That's a lot, isn't it? It is. The bad news are you have to use those 4K for not only your game logic, but also for your graphics and audio. So it's quite challenging. I struggled a lot with coding on that one. However, eventually I managed to wrap up my first game and I pushed it to GitHub. And now I get to see something really interesting. Because GitHub told me that there is this Copilot tool and it will make me 55% faster at my hobby. That's kind of interesting. So I really start to think about that. Do I want to become quicker at my hobby? And besides 55% faster at what? So how many of you have heard this claim before that you can become 55% faster with AI? So that's like 2/3 of the room. Cool. Let me ask you instead, how many have read the research paper that claim is based on? Significant drop in hands. Cool. Let's go through this together. Because I really like this paper. I think it's a very well done piece of research. It's really good. And what I particularly like about a good piece of research is that they also are very clear on the limitations behind this study. So I have highlighted a couple of these limitations from that paper. So, and you don't need to read that text. I'm going to recap the important parts of it for you. So the first important thing that they claim is that they cannot really say that these results 55% faster, that they generalize to real programming tasks, right? So that's the first thing to keep in mind. There's no such guarantee at all. Second, they also find that these techniques, this 55% faster, that seems to work for more junior developers rather than senior developers. And that's something I think is really interesting, because that kind of indicates that maybe AI can be something that can accelerate the learning. Maybe it can be an important part of an onboarding process. However, what worried me was the last part here, that this research didn't study the impact on code quality at all. And there are two different reasons why I think this is important. Because if we accelerate the pace of coding, we're going to get more code faster. So what are the implications of that? Let's think about that for a moment. I think there are two major implications. The first is a human motivational factor, while the second one touches the financial aspects of software development. So let's look at both of them, and let's start with the human side. Because I really like this quote here from Kevlin Henney, one of my big idols. And what he says basically is that if we take AI and use it to write new code, then we take the fun and creative part out of programming, and we're basically left with the much harder and more mundane task of trying to understand code that someone else wrote, in this case a machine, right? So I think this is a very valid point. However, if we also consider that we don't really know the code quality that these LLMs are generating, that will make it even harder to understand the code, right? And that makes me want us together here to question, are we really focusing AI on the right coding problem? And the reason I say this is because you have this piece of data here, this graph, that shows that today's LLMs, they're pretty good at generating new code. That's their strength. That's what they're optimized for. However, writing new code is less than 5% of a developer's work week. That's a very small part. And to put these numbers into context, if an AI can make me 55% faster at writing new code, then I save roughly 1 hour each week. I mean, 1 hour is 1 hour, right? We can use it to write Atari games, and that's a good thing. However, it's not particularly disruptive nor groundbreaking. Instead, if we look at this data, we see that the major bottleneck in coding is actually understanding existing code. So to me, there's a big opportunity here, because if we can refocus AI on helping us understand existing code, then that's the big, big win. So how can we do that? Well, let's start by looking at the potential here. I actually think we can do much better than just 55% faster. I think we can become 10x faster at software. And I know, this sounds like a ridiculous claim, doesn't it? Be honest now, yeah, it does, right? Good news are, I have some data to support that statement. And I want to share it with you here today. So take a look at this graph. So this graph is from a research paper that me and my colleagues worked on a couple of years ago. What we did here was that we measured the code quality of a lot of proprietary code. And we used something called the code health algorithm, and I'm going to cover that in much more detail in just a couple of minutes. But for now, all you need to know is that code health takes your source code and classifies it as being either green, healthy code that's easy to understand for a developer. It can be yellow, which means this code is problematic, it's hard to understand. Or it can become red, meaning it has a lot of technical debt, it's a real mess, it's very hard to understand. And what we did in this study was that we correlated the code health with the business impact, in this case, time in development. How much quicker can we implement new features if we have green code? And what we see here is that if you have green code, you can actually implement new features or fix bugs or whatever it is 10 times faster than if you have red code. So there are a number of implications here. First of all, as AI accelerates the pace of coding, I think it's really, really vital that we keep track of our code quality. Because as we see here, if an AI makes it really, really quick to generate red code, that's not particularly useful, right? So we want to kind of have some kind of guardrails around AI to make sure that the code is green. There's another reason for this, and I touched upon this earlier with both the human motivational aspect and the financial implication, that there is a significant onboarding cost associated with both yellow and red code. Here's some data from another study. We basically see that if you have yellow or red code, then it's going to take a new developer more than almost twice as long to onboard themselves in that code compared to green code, right? So imagine an AI that generates yellow or red code. It's going to take much, much longer for us to inspect that code. So code quality is really vital in the age of AI. So what I suggest here today is that we use AI to optimize for software maintenance, because to me, that's where the big, big win is. Can we use AI to simplify code? And the way you simplify code is by using a process called refactoring. So how many in the room are familiar with refactoring, the term? Virtually everyone. Really, really good. So let's break it down. So refactoring is basically the process of improving the design of existing code without altering its behavior, right? That's good. However, as simple as that statement sounds, once we start to dissect it, we see something interesting. Because what this means is that it's not a refactoring unless we improve the design of the code. And that means we need to have some ground truth, some kind of objective truth. If one version of the code is better than another, we need to know if it's a refactoring or not, right? Good. Second, it's also not a refactoring if the refactored code changes the behavior of the code. That's what we usually call a bug. The software does something different now than it used to do. That's not a good thing. So we need to check both these boxes. If we fail on any one of them, then I think the technical term for that failure is a refactoring. So, with this in mind, what we did at CodeScene was to set out and see, can Gen AI help us automatically refactor code and make it simpler to understand? And we have written a paper about it. You're going to get the link to that paper at the end of the session. And what we did in that paper was that we benchmarked a lot of Gen AI models. And I'm going to show you the results very, very soon. But before we do that, you need to know what we actually measured. Because one of the challenges here was the first step in the refactoring to find out, is the code better or not? So we need this kind of gold standard for code quality. And we choose to use this code health metric, but that's what we used for that paper that showed the business impact too, so it's the same metric. And the way that metric works is that you take a piece of code, it operates at the file level, you parse that code and you analyze it, and then you look for a number of code quality issues, a number of code smells if you want. And these code smells can be at multiple levels. You look at class design issues, module design issues, but you also look at your functions, like are the large complicated functions that are hard to understand. And finally, you look at the implementation. How much excess or unwanted complexity do you have in the implementation? Can it be written in a simpler way? And you're going to see some concrete examples later in this presentation. But anyway, we look for all these factors and several others, and then we have algorithms that can take each piece of code and categorize it based on these findings as being either green, healthy, or yellow and red, problematic. Makes sense, high level? Very good. A lot of you are nodding. I like that. So, with this in mind, we tested AI on refactoring tasks. So we had a large data lake with hundreds of thousands of known problems, known code health violations. And we instructed the AI to refactor the code. And what you see here is a summary of some of the benchmarking statistics from that paper. And let's go through this together, because we included all the big LLMs like OpenAI, Google, we had Llama from Facebook, and a couple of others. And the first thing we did was that we look at, did the LLM produce valid code? And we see that most of the LLMs, they do a really, really good job here, right? Like almost 100% of cases, they generate syntax that's valid, right? So that's a good first step. However, in the next column, where it says code health improved, so that's the first part of the refactoring, was the new version of the code objectively better? That's where we see the first drop-off. So we see here, then in roughly 30% of the cases, the LLM fails to improve the code. It just writes the code in a different way, which isn't particularly helpful. But the big drop-off is in the last column that says valid refactoring. The way we checked this was by running the unit test on the refactored code and making sure that they passed, right? And we see here that basically in 2/3 of the cases, the LLM will break our code. It will introduce a bug. So we see that the best performing LLM only produces correct refactoring in 37% of the cases. What does that mean? Well, considering having a coworker that breaks the code in 60 to 70% of all the changes they do, would you appreciate that? But for some reason, we seem to accept it when it comes to the machines. So at first, this looks a little bit depressing. But the way we choose to interpret this data is that it's actually a very good finding. Because what this means is that 37% correctness, that means we can actually fix 37% of all problematic code out there. The trick is just to know which of those refactorings are good and which are not, right? So what we decided to do was to see, can we build a fact-checking layer on top of the AI? So instead of just using the raw AI, we add some logic outside it and some models of our own. So I want to walk you through this solution. It's implemented in a product now called CodeScene. You're going to get the link to that if you want to try it out. It's completely free. So the way it works is that I, as a developer, I might write some code and I introduce some problem in it, some kind of code quality issue. What I do now is that I can ask the AI to fix it for me. But instead of going directly to the AI, what we do is we go to a model selector. Because one of the things we saw in our benchmarking data was that the AIs, they have different strengths and weaknesses. So OpenAI might be better at fixing some problems, Google might be better at others. So this model selector is basically a machine learning algorithm that knows how to select the right AI for the job, right? So we asked the AI, please fix this code. And AI will respond. We now know that in 60-70% of the cases, this will not be a refactoring. It will be something that breaks our code. So we fact check it. And the way we fact check it is by first making sure that the code health actually improves. And second, we also try to do some semantic comparison to make sure that the code now, after the refactoring, does the same thing as before. And if it fails on any of these quality gates, then we discard the solution. And we might go back and ask another AI to make a shot at this problem. And once we have something that passes the quality gates, then we know that we can propose a better way to write the code to the user, right? And as a developer, I can inspect it and apply it. Should we have a look at how this looks in the real world? Let's refactor some code together. Is this your idea of fun, to look at a piece of code on a Wednesday afternoon? Probably not. So don't worry, you don't need to look at the details at all. You only need to look at the shape of the code to know that this is highly problematic. So what we have here is a code smell known as deep nested logic. Basically, when you have if statements inside if statements, inside other statements, and then a loop for good measure, right? And the way we've implemented this is that we've implemented it as a Visual Studio Code extension. So you can get that one from the marketplace, and when you do, you see that the tool points out that, yeah, this is indeed deep nesting, right? So how would we fix this? Well, as you see here, let's zoom out a little bit. There's another option next to where the code smell is reported that says auto refactor. So that's how we choose to expose this innovation, this fact-checking layer to the user. So what I do as a user now is that I click on this auto refactor, and behind the scenes, CodeScene is going to go to a model selector, select the right LLM, get the response back, validate it, and if it's okay, it's going to be presented to me. So now the AI has proposed a better way of writing this code. And I can see that the AI has started to modularize my code a little bit. It split up this nested loop, and it introduced some better functional boundaries. So as a developer, I can now read through the code. I can make sure it makes sense and that I like that solution. If I like it, I can just apply it. And my code is now a little bit healthier. That was almost too quick, wasn't it? Let's look at another example. So this is another code smell, super common. This is something called the complex conditional. So complex conditional is simply when you have an if statement, like in this code, and inside it you have like a combination of multiple logical expressions that need to be true in order for that if statement to execute, right? So what's the problem with that? Looks simple enough, doesn't it? Well, the thing is, as a developer, I can see all the details. I can see that if this and that and so on, I can understand the details, but I have no idea what the overall purpose of that statement is. I don't know anything about the business rule behind it, right? And this is where I think Gen AI can really shine. Because an AI is very good at one thing we humans are not good at. It's good at naming things. So again, let's click on the auto refactor button and see what happens. So now again, we go to model selector, select an AI, and the code comes back. And at the top here, you see the stuff I'm highlighting. You see one of the outcomes of our fact-checking model. So we see that this fact-checking layer can now actually guarantee that not only is this code going to remove that code smell and make the code a bit better, it can also guarantee that there's a very high likelihood that this code is still correct. So I can check it and I can apply it. And once I apply it, what I see happen now was the AI took this complex expression, extracted it, and put a name on it in the shape of a function. And this sounds like a very, very basic thing to do. And in a way it is, but the benefits are huge. Because what I do now is that I encapsulate the conditional and put a name on it, and I make the code so much easier to understand. The next time I look at this code as a maintenance programmer, spending 70% of my time trying to understand the code, that process is going to be much, much quicker. So, what did we achieve? Because after building this fact-checking layer, we also benchmarked it. And I want to show you a comparison here, and I selected the GPT for that comparison, since it was one of the better performing LLMs. And what we see here is that with additional fact-checking, we can actually elevate the correctness of an AI solution from 35–37% all the way up to 97–98% correctness. And it's of course interesting to think that 98% correctness, that means that if I do 100 refactorings, 2 of them will break, right? Of course, but it's still significantly above the level of even a human expert. So by building these layers on top of the AI, we can perform at the level of human experts. So I've come to the end of my presentation. And two of the important takeaways from you here are, first of all, that AI is going to elevate the importance of code quality, right? There will be more code than ever before. We as humans, we need to understand that code. So we need to make sure that we focus on comprehending code, not just writing it, right? Because again, acceleration isn't useful if it's driving our projects into this brick wall of technical debt. And second, AI has a lot of promise to me, and it's even more promising if we focus it on the big bottleneck, the 70% of understanding existing code. And I want to show you here today how such a solution can look and what it can deliver. So before I leave time for questions, I wanted to give you a couple of references. If you want to read about the business impact of code quality, then the first link is yours. That's the Code Red paper, the business impact of code quality, where you have these graphs with red and green code. The second is the refactoring benchmarking paper, where we talk about the AI benchmarking and also the CodeScene solution to that. And finally, of course, if you want to try this on your own code, then the product is available for you. You have a link here where you can sign up and you get access to it, and you can try it out. It's completely free to try on your own code. With that said, I want to thank you a lot for showing up today and listening to me, and may the code be with you. Thank you.
Adam, Tornhill, thank you so much for that presentation. I think that was really, really interesting. I'm going to open up the floor actually straight away for some questions in the audience. I believe that we will have a lot right now. So we can start here in the front.
Hi, thank you so much for a very interesting, wonderful talk. I wanted to jump into your examples were fairly simple cases where we take one function and we make it a slightly better one function. But most of us who work in slightly bigger code bases might have this feeling that maybe it's not a function level improvement that is needed, maybe something slightly larger is necessary. What's your take on that? Is that something that we can use the AI for? Or should we start small and wait for the AI to get a little bit more capable before we get there?
Wow, that's a tough first question. It's super interesting to think about. So, yes, I agree. In many code bases, the code smells you have are much, much larger, might impact multiple modules. So my experience so far, our ambition is, of course, to take on those problems too. We are not there yet. And what I've seen so far is the AI doesn't scale particularly well to larger amount of code. So there needs to be some type of other breakthrough. That said, my experience with refactoring is that it's always really, really good to start small and clean up what we can. Because even if we focus on just these function level smells, my experience is that once we take these complicated functions and we simplify them, then that simplification in itself tends to suggest the next real refactoring step, right? That can make a big, big difference. So very often, even if the code is really, really complicated, my first steps are usually quite simple. Just try to modularize the code a little bit more. So I think that for now, I think a tool like this helps a lot with these first steps. And then we put our human expertise at the fun and creative part of solving the real challenge. Did I manage to answer the question?
Great. Let's continue on. We have a question here towards the side. Just give you 1 second, you will get a mic as well, so we can hear you.
Thank you. From the study that you presented, I just wanted to comment something and maybe ask your take on it. You said that the AI was only successful in 30% if you just use general AI, just generative AI. As a developer, I can say, maybe this is just me, but I have very rarely passed the unit tests on the first try. Usually you write your code, you think you're finished, you pass the unit, you run the unit test, they fail, so you don't commit yet. And it's kind of an iterative process. So is your AI, the ACE AI, is that iterative as well? I didn't really catch that. Like, do you go back over and over again, or to just take the first suggestion that is kind of okay?
Super interesting. So there are like two questions in that one that I think are really interesting. So The first is that the A solution is iterative, but it's iterative under the hood. So when we get these solutions, we vet them, throw away the bad ones, and look for the best option. But we don't have the full interaction with the user. It's something that we're very likely to build as well. The second thing I want to point out is that I think, I absolutely agree with you. I still write a lot of code. Good for me, unfortunately, my colleague says. But so I'm well aware of this, that it's really, really hard to design a perfect solution. You don't do that, right? It's a highly iterative process. So that's why I think that Gen AI today, even with this rather poor performance, it's useful at writing new code because it can help you with that iteration. But I think refactoring is something different because quite often the code we refactor is code that's extremely complicated, that we don't really understand. That's why we refactor it. And to change some code that we don't fully understand is a high-risk process. So that's why I think that the requirements on AI correctness and performance are much, much higher than for writing new code, if that makes sense.
Yeah. Yeah, I guess what I'm saying is that it often takes a couple of attempts to not break the code, right? And you don't commit code that is broken. So for me, when I develop, if I refactor something, I actually use the feedback from the unit test, right? Tell me that, okay, I thought I fixed it, but this is still wrong, etc. And have you... the generative AI doesn't really get that chance because we're not feeding back the results of the unit tests. So is that some research direction that you have seen or could envision? Like do you use you measure how good the model is, so implicitly you're kind of using the results, but it's just a rating good or bad, or do you feed back that data somehow?
No, it's definitely a feedback loop. We have worked a lot on elevating the AI performance because even a few percentages increase there can make a massive difference to our users. So we are constantly evaluating the AI results and trying to improve them via additional methods, of course.
Cool, thanks.
Great, let's see. Yeah, we have time for probably a few more questions. Let's take here in the front.
Hello. So purely hypothetical. Say that you're a programmer who doesn't write any tests. Is something like this possible to still give you good results, or do you need the test to kind of get that 98% accuracy?
That's interesting. So the thing is that I should have been more clear on that. The unit test was something that we used only during the evaluation, because we needed to have some kind of ground truth. Is it refactoring or not, right? But the whole purpose of driving up the AI correctness level from 37 to 98% was so that you can use it without the safety net of unit tests or tests in general. That said, to me personally, when I refactor legacy code, I always try to have some kind of safety net in terms of test, even if it's temporary, right? Because it makes a big, big difference. But yes, we have used it, and we have users that use it on code without tests too.
Great. I'm going to finish off with one last quick question. So as coders, as software developers, do we have to be worried about the future where we can be replaced by AI? And is that the reality near, or is it still far ahead in the future, in your opinion?
So I wrote about this in my book almost a year ago, because that was the time where it was as most hyped, where you had these articles like the end of programming. So I think there is a test for all of us. So the moment all of you are comfortable of stepping into an airplane that has been designed, coded, and verified in operation and driven in operation by an AI, then I think it's time to hang up the keyboard. Maybe not before.
Adam, Tornhill, thank you so much.
Thank you.